Okay. So let's look at this problem that I started a number of days ago. We're observing ships on a bay. We see 5 types of ships: tankers, sailboats, yachts, cruise ships, and transport ships. There are rules in the bay that tankers cannot follow or precede cruise ships or yachts. Sailboats cannot precede or follow transport ships. So here we've got a list of the ships: tanker, sailboat, yacht, cruise ship, transport ship. And this is a phenomenon, and we haven't asked any questions yet, but maybe we can think about a couple questions. Like given these rules, we can maybe ask a question such as, what is the probability that there will be 3 sailboats in an observation of 5 ships? How about that? If we can model this phenomenon effectively, we can answer that question. We can answer a question such as, what is the probability of seeing 2 tankers and a yacht, right? What is the probability of seeing 2 tankers and a yacht in an observation of 5 ships? Okay. So that's a question that we should be able to answer. And we can even think about these questions, right? We can start to think about them. Okay, a tanker and so what are different ways that we can get 2 tankers and a yacht in 5 ships? Well, one way might be a tanker and then a sailboat and then this might be a little bit harder than I thought. Okay, so we need a yacht, sailboat, tanker. Okay, well, can we even do this? Well, we can. So here's one way that could happen. And you can imagine another way that could happen, right? We could switch these 2 yachts with the 2 tankers and, keep that sailboat as the pivot. So we can think of offhand 2 ways where where this could happen. Given this rule that tankers cannot follow or precede cruise ships or yachts. So we've got this phenomenon, and that's where we're starting. That's our starting point. So this is maybe not the easiest thing to be able to think about. How do we break this down? How do we approach this in what I'm going to call a brute force way, a procedural way? Maybe there are better ways that we could do this, but we don't know what those are offhand. So initially we're going to take a counting approach. Why does a counting approach make sense? Well, we've got tankers and sailboats and yachts and cruise ships and transport ships, and that's good enough. That's good enough. We can count through these, and this is not pretty code, but we can do it. We can do this thing of 5 ships, right? And we can say there's ship 1 in ships, ship 2, ship 3, ship 4, ship 5, right? And we can do this thing where we append a list of each of these ships. So ship 1, and then I'll just copy paste ship 2, ship 3, ship 4, ship 5. Okay. So not all of these 5 ship instances are viable. A lot of these are not going to work given the rules that we set. And, let's just make sure that we're clear on what those rules are. Tankers cannot follow or precede cruise ships or yachts. Sailboats cannot precede or follow transport ships. Okay. So we're going to reduce out our 5 ships. And, if you saw me code this before, we're going back over it. Because this is a general approach to solving a type of problem that we don't know how to solve in a closed mathematical way. So we can take this approach and solve it, right? And that's a big power that you can have in Python, is you can, something that would be computationally infeasible that you can't do pen and paper, you can brute force it, right? As I'm going to say, you can brute force it with Python. So we've got these arrangements of 5 ships. And I'm going to say for each in 5 ships, why not? For each, I don't know. We'll just say for each, okay? We're going to assume that list, right? Or how about I do this? Ship list. How about that? That's a little better. For each of these lists of ships, we can assume that it's valid, okay? We can assume it's valid until we can show that it's not. So this is a way that we can go about this. And then we can look at each ship. We can say for I ship in enumerate. And the reason we're using enumerate here is so that we have the opportunity to compare each ship with the following and the subsequent ship. Sorry, the preceding and the subsequent ship, right? So let's enumerate over this ship list. And then we can look at these rules. We can think about these rules particularly. If the ship is a tanker, then that tanker cannot follow or precede a cruise ship or a yacht. So this becomes some conditional expressions, and so we'll approach it like that. Okay. So if the ship is a tanker, right? We're translating from informal language into formal language here. If that ship is a tanker, then we're going to do some things. We're going to first consider if that tanker is in the first position, right? Is it the first ship that's going by? Because if it is, then well, how about this? If that ship is a tanker and I is 0, then the following ship cannot be a cruise ship or a yacht, right? So how about this? If I is 0, we'll start there. So if tanker is in the first position of that list, then ship list sub I plus 1 cannot be, so it cannot be in yacht or cruise ship, right? It cannot be in that. So I'm just going to make this a compound expression. Yeah, how about that? So if I is 0 and ship list sub I plus 1 is either yacht or cruise ship. So we've already established the ship is a tanker, and the next ship, if it is either a yacht or a cruise ship, then we can say that this is not a valid arrangement. Okay? So that takes care of one condition. And then in all other conditions, we need to, well, not in all other conditions. How about this? Let's say elif I is not equal to 4. How about that? So in this case, if that tanker is in the 4th index or the 5th position, then the preceding one cannot be actually, how about this? That needs to be tabbed in. Let's think of a different condition. Okay, let's say I is 4. In that case, we can slightly modify this and say, and ship list I minus 1 is either a yacht or a cruise ship, then valid will get false. Okay? So you might be thinking of your Boolean logic right now. But we'll leave this in a long form. And otherwise, we're going to think about this tanker. We've already covered the condition where I is 0, and we're looking at the next one. We've covered the condition where I is 4, where the tanker's in the 5th position, and we look at the previous one. And in all other cases, we can we should be able to look at whether or not if ship list I plus 1 is in yacht or cruise ship, or ship list I minus 1 is in yacht or cruise ship, right? We already know it's a tanker, so we need to eliminate these other two possibilities. If either of those things is true, then valid is going to be false. We are going to invalidate this. Okay, so I think that takes care of our tanker. Let's just run this. Their rule, tankers cannot follow, so I'm just going to cross this out because I think we took care of that. Let's run this as it is, and if valid stays true, right, for a particular ship list, then we want to collect that ship list, right? So if valid, then we want to collect that into this possible 5 ships. Possible 5 ships, dot append, and we'll append the ship list. Okay. Again, this is only one of the rules that we have to satisfy, and we'll work on satisfying the next rule. So let's just snag this whole line, and let's look at some output just to make sure that there isn't a glaring error or something like that. Let's just make sure that we're on the right track. Okay, so let's print that ship list. And the assumption here is that this is going to be pretty long. That's okay. So let's run Python tiprep.py. Oh, list index is out of range on line 31. Let's solve that. If ship list I plus 1 in yacht or cruise ship. Okay, so if I is 4, I is 0, I is 4, I plus 1, I minus 1. Interesting. the ship is a tanker, then we start doing this stuff. And if I is 0, if I is 4. I see. It's because I'm still allowing for situations where like what I'll do instead of this, I'm going to do a nested list. I think this will be actually a better way to think about this, and we'll do that. Yeah, this way we're not satisfying two conditions. Because in cases where we're not dealing with 0 or with I being 0 or 4, we actually want to be able to how do I say this? If the tanker is in a position other than 0 or 4, then we want to perform these two conditions. But we don't want to we don't want to exclude situations where if I have that and in there, then we're going to run the else much more often. And we're going to have an index of 0 at times where it's not 0 and this other state of being. So there we go. All right. So what we shouldn't get is tankers preceding or following cruise ships or yachts. So let's just scan through here and look at some tankers, and hopefully, so tankers, I don't see tankers in relation to cruise ships or yachts. Here, here, or here. I think we're probably doing okay. Yep, I think we're probably fine. And, here's a tanker in relation to sailboats, tanker. So, we could have a more formalized approach to making sure of this, but I think we're fine. I think we're doing okay. Okay, so we looked at one rule, tankers in relation to cruise ships or yachts. Let's look at sailboats in relation to transport ships. So we have this other condition, and I don't need to do an elif here. I'm just going to do another if. So if ship is sailboat, then we're going to do something else. Okay. So in this case, this looks a lot like this, right? If I is 0, then we're going to look at the next ship. Okay. I can actually just kind of copy this whole set of rules. And instead of saying ship list I+1 in yacht or cruise ship, I could just make this a single list and say transport. That's a little bit, I don't really need to do that. I can do that. So I'm going to replace these in statements with these equivalent statements. Okay. So I think that logic is solid. We can find out. Might be something a little off here, but I think this will work. Okay. So let's run it. And transport shouldn't be in relationship to sailboats. Transport ship. That's important. Let me just fix this wherever it occurs. Okay. Okay. So we shouldn't see a transport ship in relationship with a sailboat, or a sailboat in relationship with a transport ship. And I think we can be pretty certain about that right here, right? Because we've counted up to transport, 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 but none of these say sailboat. We do have a sailboat in relationship, like one away from a transport ship here, but that's okay. There's no rule against that. If I look for, wherever sailboats are, notice we never see sailboat and then transport. So I think we're doing good. I think this should be working. So that may seem like a lot of work, and it is. And it would be really hard to do that work on paper. But turns out a computer can do this really well. It's not that hard. And we didn't need to write super nice code to do it. We just had to break out our logical thought process here. So now we've got our possible 5 ships, and we can try to answer these questions. So what is the probability that there will be 3 sailboats in an observation of 5 ships? So 3 sailboats. And then I can say for ship list, right? I can just use this. For ship list in possible 5 ships, I'll say if ship list dot count of sailboat is equal to 3. Then we'll print the ship list, but we'll also collect it so we can see this in real time. 3 sailboats dot append that ship list, and the probability of this is going to be the cardinality of A, which is 3 sailboats, over the cardinality of S, which is the length of the possible 5 ships. Okay? So barring having done something wrong here or having some error in here, we should see a result. Okay, so it looks like there's a 7.3, 7.4% chance that we're going to see 3 sailboats. Does that mean 3 sailboats in a row? No. It just means 3 sailboats total. And here are all the ways that might happen. And so we can look at these to kind of verify that these make sense. I think we're starting... Not there. I guess we're starting here. This looks right. I should probably put... I see what's happening. There we go. I was printing something extra that didn't need to print. There we go. Okay, so if we look at this, we can see these different ways that this might happen. Tanker, tanker, sailboat, sailboat, sailboat. Tanker, sailboat, tanker, sailboat, sailboat. Tanker, sailboat, sailboat. I'm not going to read through all these, but we can see how we've reduced the space. And I think that's important. We can take a look at it. And then we get a probability. That probability, again, is just the cardinality of the subspace, 3 sailboats, over the cardinality of the sample space, possible 5 ships. Okay, so that's a way we might answer that. And I will answer this next one. What is the probability of seeing 2 tankers and a yacht in an observation of 5 ships? So this is really kind of the same question, but we're going to answer it slightly differently. So 2 tankers and a yacht. And for the ship list and the possible 5 ships, if ship list.count of, I think it's just tanker, isn't it? Is that what I did? Tanker, yeah. Okay. .count of tanker is equal to 2, and the ship list.count of yacht is equal to 1. Then we can print that ship list, and we can say 2 tankers and a yacht. We can append the ship list. Now, there might be a little bit of vagueness in here, right? Do we mean a yacht, at least one yacht? Or do we mean a single yacht? That's a not great thing about these sort of probability questions. I am not sure which I meant. And so what I'm going to assume is this, at least 1. So I'll change this to be greater than or equal to 1. All right. So we need at least 1 yacht in there. And you can imagine there's a scenario where we have tanker, yacht, 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 tanker, or tanker, tanker, yacht, yacht, yacht. All of those possibilities, all of those permutations should be, part of constructing this probability. So if we want to answer the question regarding probability, that's easy. Again, that's cardinality of A over cardinality of S. Same kind of probability approach that we've been talking about. The subset over the superset, or the sample set, and we should just be able to see this. Let's find out. Okay, something like a 0.04 probability, 0.041 probability. And we can look at some of these: yacht, transport, tanker, right? There's 2 tankers and a yacht. We can see that that is the result in all these cases. So that is an example of modeling a phenomenon and seeing the results. So I'll paste this code in, and let's think of another problem. But before we do that, are there any questions about this approach? In terms of Python, one of the tools that we're using here is using for loops to count, right? That's what we're doing here. We've gone over that quite a bit, but if there's any confusion of what's happening there, please let me know. Then we're reducing out the space. Again, we need for loops. I'm using a Boolean flag here. That's really helpful in this. There's probably a way I could do this without a Boolean flag, but I think the Boolean flag is very helpful here. I'm using enumerate. The reason I'm using enumerate is that I need to know where the ship is, where this item is in relation to other items. And so, I get the index out of there, I get the item out of there, and then I can compare based on that index. And beyond that, we're counting items. That's all we're doing after that point. Now, if we wanted to answer a more complex question, such as what is the probability of having 2 sailboats in a row? Okay, well, that's a different. We would have to think about that in a different way. But shouldn't be too hard to think about how to approach that kind of problem. How do we find out if there are 2 items in a row? Let's not worry about that for this. And I'm going to, let's think of a different kind of problem. And maybe we can think about this. Let's bring it back to something based on dice a little bit, because I think that can be fun. So let's imagine a scenario where maybe we're building a model to look at bacteria, and these might be bacteria that consume each other in some way. So that, let's think about this. Yeah, okay. I think I know a good way to do this. Okay. So let's take this step by step. I'm going to have you write a function. Write a function called dice roll. Okay? There's one parameter, so this takes one argument. That is the number of sides. All right. And what this should return is should return a random side from the roll of the n-sided die. Okay. All right. So you're going to find random choice to be helpful here, right? From random import choice. And then, yeah, see if you can define this function. Let's put 4 minutes on the clock for this. And then we'll expand from there. Okay, so let's look at how to write this. And whatever you have, go ahead and paste it in the Slack. If you felt really stuck on it, if you didn't get started at all, that's okay. But yeah, let's just look at a way to write this. So we'll need the choice function. So I'm going to say from random import choice, easy. And then I'm going to say let's make a dice roll. And I'm going to pass in the number of sides. I'm going to define that parameter. And then we can just return the choice from a range between 1 and the number of sides plus 1. So, you know, I just combined a few things here. You know, we could break this out. We could say, you know, possible rolls, right? Do that. That'd be fine. But I'm going to go ahead and keep this as one single function. So let me paste this in. And let's expand on this idea. So I'm going to have you write another function. So this will be a little more complex, okay? So you're going to write a function called series of rolls. And it's going to take a list called dice sides as an argument, but that's what we define as the parameter. The list should contain the sides of the dice that will be used in subsequent rolls. Okay. The function should return the list of rolls in order. Okay, this might be a little confusing. You know what I'm asking for here. Imagine we have, here's an example. The list of dice sides that you pass in could look like something like this. We have a 6-sided die, then we have a 12-sided die, then we have a 24-sided die, an 8-sided die, and a 4-sided die. So that's what we pass into the function, and we get out of the function. The returned list could look like this. With that input list, well, the returned list, maybe we roll a 3 from that 6-sided die. Maybe we roll a 12 from the 12-sided die. Maybe we roll a 4 from the 24-sided die, a 7 from the 8-sided die, and a 2 from the 4-sided die. So notice here that we cannot exceed on any one of these rolls. We cannot exceed the input, right? We can't exceed the number of dice sides on any of these. So that function is a little more complex. And why don't we let's do 6 minutes on this. Think about how to do this, and you know, try to get it to work. It's okay, really okay if you don't, but put your code in, whatever you get. So I'll go ahead and start this and see if you can code that up. Okay, so let's look at a way to do this. Let's see, I called this series of roles. Yes. And let's just do def series, make this a little bigger, series of roles, and we'll pass in these dice sides that are lists, although we could assume they're tuples, doesn't really matter. We could return lists or tuples, but let's go ahead and just keep with lists. So for whatever in, or so, sorry, for I in dice sides, this will be, let me just call this sides. For sides and dice sides, we can just say list.append, and we'll append a dice roll based on that side, right? Based on that number of sides. Okay. We should, at that point, be able to return a list. And let's test this. So let's do series of roles. And actually, let me do it like this. So I'll call this sides, and let's do 6, 12, 24, 8, 4, 64. Okay? Sides. And we'll see if that works. Okay, so let's print. Well, we don't need to print the sides, but let's look at the result of this. Transport ship, yacht, transport ship. I need to comment something out. But here's one result, right? 2, 4, 18, 5, 1, and 22. And if we look at that in relation to this, 2, 4, 18, 5, 1, and 22, that looks pretty promising to be working in the way that we might expect. Okay. Let me figure out what is printing out up here. It's that. So let me comment out that. I think there might be another one up here. And this is another good reason to wrap everything in functions so that you don't just have some massive wall of stuff that's doing things. Okay. So we have this function and it works, and I think we can now use this to try to model a fairly complex idea. Okay. And bear with me in this idea. I think it'll be kind of fun, and hopefully it'll illustrate the kinds of mental models that we can put together and explore with Python. So let's say we're modeling the interactions between a couple of bacteria, and let's think about this. Yeah, let's think about this as this. So we're modeling a battle between bacteria. We're modeling battles. Battles doesn't sound very scientific. How about interactions between bacteria in an experimental environment? How about that? The bacteria have a series of characteristics that will determine whether or not they survive when they interact with another bacteria. Okay? These characteristics are represented by a series of dice rolls that will be output as a list, and how about we say that the lengths of the bacteria lists will be the same. Okay, so there's kind of our mental model, and let's take this a little further. Take the idea of this a little further, and maybe I'll just, in case anyone wants to read back through this, I'll just put it in the top right corner as I go forward. So to continue with this idea, let's say bacteria 1 has these attributes. And that'll be, how about 6, 8, 9, 12, 2, and 1. And these are, that's a 6-sided die, a 9-sided die, a 12-sided die, a 2-sided die, and I don't know, a 1-sided die. Obviously, there's only one thing that can get returned from a 1-sided die, and that's the value 1. Okay, so let's say bacteria 2 has these other attributes. Let's say it's 2, 18, 25, 1, and 2. And so, you know, offhand looking at this, is it clear if we're randomly battling, right? Here's a 6-sided die versus a 2-sided die. This 6-sided die is much more likely to beat the 2-sided die, right? 18-sided die more likely to beat the 8-sided die, 20 more likely to beat 9, 12 more likely to beat 5. We can kind of see that, you know, we can kind of imagine, are these well matched? Or does one seem like it's going to do better? It actually seems to me, offhand, I don't know this, it seems like bacteria 2 will do better. That's okay, we'll find out. We'll figure out a way to go about this. So what this might mean is that, let's say bacteria's 1 and 2 roll. How about this? Let's say for each of these, we score whether or not bacteria 1 or 2 gets the higher roll, okay? And if bacteria 1 gets the higher roll, then you know, gets more wins. How about that? Gets more wins than bacteria 1 wins the battle, the bacteria battle. Okay, so we're going to have some kind of score out of this between these different sets of dice rolls. Obviously, the highest score one could achieve if you have a length 6 list is the score 6, right? The highest score, and yeah, so let's just be clear about that. And more likely it's going to be something in between. So we have, let's say we have scores like this. You know, let's say bacteria 1 scores 3 and bacteria 2 scores 1. Well, then bacteria 1 lives, bacteria 2 dies. So that's an approach we could take. And maybe we take this approach, right? Or maybe we could do something a little more fun and have it be, you know, the differences of the scores. That might be something a little more interesting, right? Like if bacteria 2 rolls a 12 on this 18 and bacteria 1 rolls an 8, then, you know, basically this 8 goes down to 0 and the 18 goes down to 4 or something like that. We could do this in a number of different ways. But let's try to keep it simple with this. So what I'm going to do is, in my very scientific language here, I'm going to write a function called bacteria war, okay? Bacteria war. And I'm going to pass in bacteria 1 attributes, okay? And bacteria 2 attributes. And I'll make this a little smaller so we can see it. And I'm going to try to code through something that models a battle between two bacteria. Oh, and let's say that if the scores are equal, then both of them die. How about that? Let's say scores are equal, both bacteria die. All right. So given these attributes, we've got a function that will get us dice rolls, right? So we've got a series of rolls. So I'll grab that name, and we can have our back one rolls, right? Series of rolls, and these are our back one attributes. And back two is going to be similar to that, right? Back two gets series of rolls, back two attributes. And we can create a score list. And I'm going to write this in kind of a longhand Python, just to, hopefully to keep it easy to break down. So we've got back one and back two. These are the actual roles that have been committed. So one way that I could do this, if I want to compare these to each other and tabulate the scores, I could say, well, let's do this using zip. Well, let's not use zip. I like zip, but let's skip it because I don't know how heavily we covered it. Let's do it like this. For whatever in range, no, sorry, for I in range, the length of the bacteria 1. Remember, bacteria 1 and bacteria 2 should have the same lengths in terms of their battle stats. So we're not gonna safety check that or anything like that. And I'm gonna say if back 1 sub I, if that roll is greater than back 2 sub I, then I'm going to append to this score list that bacteria 1 won the battle. How about that? That's one logical way that we could do this. There are others. There are other ways that we could do that. Here's another case. Let's say bacteria 2 wins. Then we can append a 2. And in all other cases, we can append a 0. All right? So at that point, we can figure out which bacteria won, right? We can say, and we want to return the attributes of the winning bacteria. And how about in all other cases, we return a list of ones? You know, if they tie, let's return a list of ones. Let's just do that. Okay, so if score list dot count of 1 is greater than score list dot count of 2, then let's return bacteria 1 attributes. And we've got another case where this is reversed, where we'll say elif bacteria count of 2. Well, let's just flip that. And in that case, we'll return the bacteria 2 attributes. And in all other cases, let's just return all ones. So that's just a shorthand. That'll get us a list of ones that are of the length of that bacteria. So, okay. So I think that'll work. Let's grab these attributes and test this out. So let's do that. There's our bacteria 1 our bacteria 1 attributes. Let's get our bacteria 2 attributes. And now let's see how they go up against each other. Hopefully this will work. I mean, I think it'll work. It might have an error. There we go. Count takes exactly 1. Argument 0 were given. That makes sense. That should be a 1. Okay. So looking at this, it looks like bacteria 1, 1. 6, 8, 9, 12, 2, 1. Let's run that again. 6, 8, 9, 12, 2, 1. 1 wins again. Wins again. Wow. 1 seems to have won a bunch of times out of those 4 times. And or 5 times. And then bacteria 2 finally won. Bacteria 1 again. Bacteria 2. Bacteria 1. 1. 2. 2. 1. You know, we could run this all day. But there are better ways that we can figure out overall how, you know, one set of attributes fares against another set of attributes. And that would be through, you know, running this experiment a bunch of times. Okay? So let's take a 5-minute break. And when we get back, we will do that. We'll run this experiment a bunch of times. And I'll give you this code. So you've got that. Yeah, let's take a 6-minute break actually, and I'll see y'all back here in just a little bit. Okay, so let's continue forward with this idea. We have this function that essentially will give us the results of what we're calling a battle between two bacteria. Okay. Now, we didn't need to make this about bacteria. We could have used any other situation, right? We could have talked about these as attributes of some D&D, some tabletop style game. It could be anything. That said, we were running this function over and over again with these two sets of bacteria attributes, and what we were discovering is it seemed like bacteria 1 was winning more, but we didn't really run this enough times to really tell. And so what we might do at this point is try to get a more definitive sense of what these outcomes might be. So I'm going to start coding a function. I'm going to have you guys finish it. I'm going to say bacteria war outcomes. And we're going to pass in the bacteria 1 attributes, bacteria 2 attributes, and some number of samples. Okay. And I'll define the dictionary that we'll use to collect results. And we'll have, let's see, bacteria 1 wins. And we'll start that off at 0, obviously. Bacteria 2, start that off at 0, and both die. And we'll start that off at 0. Okay, so that's the snippet that you're going to start with. And what you're going to do is populate this dictionary with results of these samples. Okay? So I'll put that in the Slack. That's a snippet to start with. And let's do... let me think about this. Let's do 5 minutes on this. Okay? All right. Do your best. Wherever you get to on it, go ahead and paste it in. And yeah, see if you can make this happen. Go ahead, paste in whatever you have at this point, and I'll walk us through a way to do this. So this is just our sampling pattern that we've been doing. So I'm going to say for whatever in range, and we're going to do that num samples times, right? So whatever in range, num samples times. And what are we going to do? Well, we want to get the results from a bacteria war, right? So I'm going to say results of the bacteria war, pass in the bacteria 1 attributes, the bacteria 2 attributes, and that should give us the list of the attributes that would win. So if that result is the same as the back1 attributes, then we're going to say d sub back1 wins is going to get incremented. If the result so I'll say elif, the result is the same as the bacteria 2 attributes, then bacteria 2 wins. And in all other cases, we're going to just say d sub both die. Okay, so we're doing this. Let's by default do this 1,000 times. I didn't put that in the thing, but seems like a decent number, and we can just return the dictionary at that point. Okay, so let's traverse the dictionary and see what we get out of this. Get a dictionary, and we'll say for key value in d.items, and here's this pattern that we see all the time. Print the f string of the key and the value. And we'll get a little table showing us what the results are. The results of running this a bunch of times. Bacteria 1 attribute is not defined. On line 183. Oh, well, that makes sense. I think I'm just calling these back 1 and back 2. I'll grab these. Oh, I guess we want them up there too, in case we come back and look at it. So I'll just put this here, and I'll change these items just a little bit. Bacteria 1, bacteria 2. Okay, so d sub both die. Let's see. What error are we seeing now? 125. Back 1, back 2, num samples 1,000. Huh. Oh, key error, both die. Well, that's because I put 2 extra spaces in there, so it all line up. I don't know. That makes absolute sense that didn't work. Okay. Key error back 2 wins. Oh, that's because I didn't define that key. So I think that might be the last. Yep, there we go. All right, so, we had the impression that bacteria 1 was winning more. Turns out it was. It was. That wasn't just, we observed this a few times, and we're like, okay, well, bacteria 1 seems to win a lot more. And let's run this again. You know what? They're doing pretty reasonably similarly here. 374 to 362. Is there a case where bacteria 2 is going to win the majority of the times? It doesn't look like it. And I imagine if we do this 10,000 times, we'll get something a little more surety here, right? We widen that gap. We go from 360 versus 379. We go to 3,400 to 4,000 roughly, and so there are a lot of cases where they both neither of them makes it, but the vast majority or the increasing majority as we do more samples is going to be bacteria 1 winning. Now we might want to think of why. Why is that? Is it simply because there are more instances with these attributes where we have more dice, like 6 versus 2, that's one, bacteria 1 has more sides in 1, 2, 3 cases, but bacteria 2 has more sides in 1, 2, 3 cases. So why, can you think of a reason why bacteria 1 would generally be outperforming bacteria 2? I think it's a good question. And it's the kind of question that maybe we can't answer right now just looking at this. But let's think about the sum of these sides. And maybe what we want to say is that let's see what kind of results we get if we just pass in, instead of those original lists 6, 8, 9, 12, 2, and 1, what if we pass in a list that only has a single item? This will still, I believe this will still work. And let's see if which outperforms the other, bacteria 1 or bacteria 2. Let's find out. Well, in this case, bacteria 2 wins. So it isn't just the raw sum of sides that is leading to these wins, right? So, it's still a little mysterious. And honestly, I don't know offhand. Let's try to increase one of these sides. Let's change 20 to 200. And this is the kind of exploratory thing you might do in these kinds of models. Okay, well, clearly, if I change one of these sides in bacteria 2 to 200, bacteria 2 will win a lot more. But we have a lot of instances where they both die still. And I think maybe this is going to stay a little bit mysterious. But in general, with these attributes, bacteria 1 will win. I'd almost throw these two away, this 2, 1, and 1, 2, and just look at these first 4, and we can start thinking about them. It might be that in almost any case, 6 is going to win over 2. Right? If you think about it. In almost every case, 6 is going to win over 2. And so it might be the percentage, the ratio of one attribute to the other attribute that is accomplishing this. So there are a number of cases where 8 to 18 or 9 to 20, right? Where these are going to come out, where, let's say, bacteria 2 is generally going to win against these, but these are nearly, 50-50, there's a 2 to 1 chance here that bacteria 2 will win, 2 to 1 chance here that bacteria 1 will win, but then this first one is maybe just more of a sure thing. So maybe let's hedge our bets and change that 2 to a 3 and see if that really sways things. It seems to. It really does seem to sway things quite a bit. And I think, if we run this a number of times, in general, it's this first value that is leading to bacteria winning. The 6 to 2. Okay, so, that's pretty involved, all of this. This is something that, we can take an idea, invent an idea, explore that idea. That is within our scope of things that we can do. So let's do something a little different. Let's move on to maybe a different type of problem. Let's think of something maybe a little more mundane. How about... I think I actually have something I can refer to on this. Okay. Yeah, here we go. I think this is something we can look at. It's another sort of problem in this type of problem, okay? So let's say we define a random variable y, okay? Let's say y is the result of rolling a 4-sided die, then a 7-sided die, so we'll stick with dice for right now, then a 12-sided die, and then processing it through this function, okay? So y is going to be d4 cubed plus d7 squared and multiplied by d12, well, the square root of d12, okay? So the first thing we might do here, well, we can unpack this problem, right? We can turn this into a function. We can say, I'll just call this roll math. It's my fairly uncreative name for these kinds of functions in general. It's just we roll some dice and we do some math. So we have roll math, and we're going to put in a list of rolls. So I'll call that roll list. And D4, D7, and D12 are going to come from that roll list, okay? And then we can just return this result. Okay. Oh, did I paste in... I'm sorry, let me paste in the results of this prior function so that you have it all kind of in the same area. Okay. So we pass in the result of 3 of these rolls, and luckily we have a function that we can depend on for this. If we want, we can adapt a series of rolls. I'm actually just gonna do something a little more boneheaded for this. We'll still use random choice, but I'm not going to use the prior functions. I'll try to keep these kind of separate from each other. Okay, so here we've got this function, roll math. And we might... So this is kind of the entirety of our phenomenon, in a way, right? Although we need some way to definitively answer certain kinds of questions, right? Like, say... Let me ask a couple questions. What is the probability that y is less than or equal to 80? Or what is the probability that y is greater than 50, right? Like, these are the kinds of questions that we might try to answer, okay? Now, this is coming from a place of not really knowing what what our resulting distribution will look like. Or even knowing if these numbers are reasonable, less than or equal to 80 or greater than 50. So how do we start understanding our distribution? Well, we only have dice 4, dice 7, and dice 12 here. This is a good candidate for a counting approach, right? So we can take a simple counting approach and start figuring this out. So let's use counting. And this will help us to determine just some basics about our distribution of y. So I'm going to say outcomes of y. Let's say for D4 in range, and this will be 1 to 4 plus 1, right? And then we can say for D7 in range, and 1 to 7 plus 1, right? And then for D12 in range, we can go to from 1 to 12 plus 1, okay? And then we can append to y, outcomes.y.append. We can append the roll math from D4, D7, and D12. This is going to be every potential outcome, okay? And we might want to reframe these questions after seeing this. So let's just take a look. For list in outcomes of y, let's print every item in that list and see what we get. Not sure why I'm getting a warning on these. Whatever. It's probably fine. Name outcomes y is not defined. Oh. There we go. Okay. Roll list is not defined. Roll list, not LST. Okay. So remember those first couple questions that were kind of exploratory questions. What is the probability that y is less than or equal to 80? Probability that y is greater than 50. Well, we can probably start, we can observe maybe what's going on here a little bit at least. I'm not even seeing any numbers. Well, I'm seeing a couple numbers less than 80, okay? So that's not bad. 73 is less than 80. 68 is less than 80. 65, okay. So we've got all these numbers in no particular order, right? So we can go from there. We have this y outcome, and I guess we can start thinking about answering these questions. So we've got these two questions. How do we start going about answering them? It's not too hard. We can say less than or equal to 80, right, is, we're going to look at a count of those. Greater than 50, do GT 50, do a count of those, and we can look at each value for value in outcomes of y. If the value is less than or equal to 80, then LTE 80 is going to get incremented by 1, right? So that's one condition. If the value is greater than 50, greater than 50 gets incremented by 1. Notice I'm not answering these questions separately, but they're kind of unrelated questions, but I can use the same for loop to approach each of them. So let's print, I'll just do this less than or equal to 80, and we'll put this in like so. And we'll do that again for greater than 50. Greater than 50. Okay. All right, let's see what we get. So we're getting counts here, not probabilities. I actually meant to get the probability out of here, but that's easy enough to do. It looks like less than or equal to 80, there's 140 of those. Greater than 50, there's 241 of those. Let's actually calculate these probabilities. So less than or equal to 80, it's going to be divided by the length of the outcomes of y. That's easy enough to do. And we'll do it for both of them. Should probably round it, but let's just see what we get. Okay, yeah, let's round that to 4 places, or 3 places. Notice these are definitive. These are the actual probabilities of the theoretical distribution, right? They are, you know, we're not taking a sampling approach here. We are answering questions directly. So it looks like there's a 0.44 probability that we get a value less than or equal to 80. There's a 0.717 probability we get a value greater than 50. Okay. So this is all well and good. Y is this kind of abstract concept that looks like this and has outputs that, you know, we're not totally clear on why this math works out this way, right? We're summing the cube of a D4 and the square of a D7, and we're multiplying all of that by the square root of a D12. We can think about why that might be. You know, I don't think we really need to offhand. So, yeah, just think about, just realize that this is an obtuse process that we're looking at here, an obtuse phenomenon, and we can still analyze it. We can analyze it through a counting approach, which is, you know, which is nice because it gives us very clear answers on our probabilities. So we can do other things here, all right, to analyze this. We answered a couple questions, but we can do other things. We can get the min, right? So let's get the min and the max. If we're really trying to understand this distribution of y, we might take this approach. And we might say def get min and max. We'll pass in a list, and then I'm going to say return the min of the list and the max of the list. Okay? And let's get the min and the max of the outcomes of y. And, you know, this is going to vary upon... No, it's not. Sorry. This is not going to vary on our runs because we've counted, right? These are counting approaches. 2 is our min. Okay, well, how do we get 2? How do we get 2? Well, let's look back at this. This could be 1 plus 1 times, well, 1 plus 1 times 1, right? That's 2. Well, that makes sense. So suddenly our process here is a little less obtuse. We can see why we got that min. Now our max is 391.443, right? That we might not be able to clearly solve through this, but you know, we could take this and we could put in our max values and just see what that is, right? So this would be this is our D4, so 4 to the 4th, 7 squared, and the square root of 12. And just as a one-off, is that going to be 391.443? Well, let's find out. It turns out it is, right? So clearly, our min and our max values are the results of simply putting in the min and the max dice rolls for all of these. Okay. So in this case, Python helped us illustrate and flesh out part of this idea. Okay. So if we're going to analyze this, there are ways that, well, there are ways we might want to go about doing that. And the way that I would think offhand to do that would be to use a dictionary where I make bins, okay? And I'm going to make a bins dictionary, and we're going to pass in, well, let's not pass in anything. Well, yeah, let's pass in our outcomes of y. Since we already have it in the general namespace, let's just do that. And we're going to define a dictionary. And we're going to say let's populate this dictionary with values, okay? So I'm going to say for num in range, I'm going to go from 0 to 401. And why am I choosing 401? Well, 401 is 10 more than 391. I don't know. It's just a number I'm throwing out there, and I think it will be sufficient. And let's go by tens. Let's make these bins in increments of 10. All right? So if num is 0, I'm just going to continue. Why not? So we'll skip that first bin. And I'm going to populate the dictionary like this. So I'm going to say num minus 9. So this is actually going to start off at 1. And it's going to go up to num. So offhand, this is going to be 1 to 10. Okay? And I'm going to start my counts at 0. So I'm dropping these numbers into bins. Okay? So why don't we just take a look at what this dictionary looks like. I'll call bins dict on outcomes of y. And see what we get. So we've got this nice dictionary, 1 to 10, 11 to 20, 21 to 30, 31 to 40, 41 to 50, and so on. Okay, so from here, I'm going to say for each value in our outcomes of y, I'm going to round that value. And this is an easy way, okay? This is an easy way to sort of drop something into a bin, and I think that'll make things a little simpler. So I'm gonna round that value down, and then I'm gonna say for k v in d.items, I'm actually gonna traverse the dictionary, and if at some point this value makes sense in terms of fitting in the range of the key, then I'm going to increment the value. Okay. All right. So I'm actually going to break this key out, and this may seem like some evil magic I'm doing here, but it's actually pretty simple. It's pretty straightforward. So I'm going to split on spaces, which means I'm going to get this low value, let's say 1, and the high value. So I get 1, throw away this word 2, and then for high, I should get 10, I believe, on this first one. Okay? So that should be 1 to 10. Okay. So if my value, right, if this value up here, not this v, if this value up here is greater than or equal to the int of low, right, and the value is less than or equal to the int of high, right, that's what the other one, because these are strings, I need to cast them to ints, then I'm going to say d sub k plus gets 1, okay? And at that point, I can return the dictionary. I can just return it. So that should populate this effectively. And now we can say for key key and value in Bin's dictionary on the outcomes of y. Let's print, and our familiar construct of the f string, printing the keys and the values. We can see, hopefully this will be in order, I think it should be. Too many values to unpack, expected to, for KV and Bin's dict outcomes.y on line 263. Oh, I always get this error. Now I always forget that I always get that error. Dot items. Okay, here we go. All right. So here are our kind of resulting binned values. 1 to 10, got 18 values there. 11 to 20, 19 of them fall in there, right? And we're seeing kind of a peak here around 21 to 30, and less as we head up to 391. So turns out that most of our values are falling in this lower part. And it looks like this, if we think about what this distribution might look like, it might be something like, you know, sorry, I was going to draw on there. It might look something like that, okay? Where, you know, got the majority of our values in there, and then we sort of trail off as we go off to the right. And, you know, it's not a perfect, it's not like a smooth distribution like this either, because we have some jumps, right? We've got some jumps in when we get to 171 to 180. We've got a few more values that end up there. We've got some fluctuation out here on the end. You know, 31202. We've got some missing areas as well. So, you know, in this bins approach, we don't necessarily get the best representation of, we don't get the perfect representation of these values. But I think since we have discretized it, we get something that's a little bit easier to interpret, a little bit friendlier. We can describe it a little bit better. Like most of our values, right? Most of our values are sitting up here in the, you know, between 1 and 100, really. 1 and maybe 130, actually. So hopefully, you know, these kinds of problems, and we're going to do more of these. We're going to do more of these on Saturday. These problems are in the family of problems that look like the technical interview. I don't want to say that these problems are on the technical interview or you'll see something exactly like this. You know, likely not. But we will look at, we're going to take this same idea and bring it back around to the discrete distributions problems, as we've talked about already, and do some review on those. But the main thing is we can take real world scenarios and we can model them in a way that gives us pretty clear probabilities. Like we can model situations and we can make things up. You know, not to say that flippantly, but we can make up, you know, some type of experiment where we model, you know, bacteria's in some way, you know, and you know, maybe it's a little bit of a stretch. You know, maybe there are certain organelles that one bacteria has and another one has it too, but they're different bacteria, and you put them in the same place and maybe one consumes the other, or they try to consume each other or something like that. And the presence of those organelles makes a difference in that. And so we have some observable phenomenon that we've recorded data on, and then we model that phenomenon with a computer simulation like so. And, you know, it's probably not going to be like dice rolls per se, but it could be, you know, we could approach modeling, simulating that kind of situation using raw Python like this. It's not out of the question. In fact, it's something that's done quite a bit. And then ultimately we have some kind of abstract math problem on a random variable, right? We define y, and we do some math on it, and we don't know what that distribution is going to look like. This isn't a known distribution. We just invented it, and we could change this math, right? We could change this dramatically, right? I could say divide this instead, right? And if I run this again, comment this back in, and I think we're going to see an extremely different distribution, and that shouldn't be surprising. And not just extremely different, but almost all of our values are below 30, right? And these bins are probably too large. And the thing is, we could take we could think about this as any number of different mathematical formulations, and this pattern will work, right? This pattern will work in the analysis of that, and we can gain a lot of insight into those formulations. So, yeah. Try to go over this code. I'll share this file one more time. I think I have it somewhere. Link to it somewhere. Yeah, I'll put this in the Slack. Try to understand. Try to understand these. Try to invent something like this, right? Try to take a mathematical concept that you know or that you just invent on the spot and analyze it and try to understand it. These patterns are pretty common. We've got a sampling pattern up here with the bacteria approach. We've got two different counting approaches. What we didn't do in here is use any closed form, any formulas, but that's okay. That's something that we can always do. But yeah, there's some logic in here to pick apart, right? Especially in this 5 ships. Understanding why this logical structure works. Thinking about how you might simplify it. These are all things that if you practice this kind of thing, you're going to become a much, much stronger coder. And you're going to be able to solve questions. Even if you don't know how to do it quantitatively, you can do it procedurally. And that's really important to understand. I purposefully came up with some problems here that I don't know how to answer these outside of being procedural about them. Not offhand. I'd have to sit down with it for a while to think out the math. But, my recommendation is to figure out how to do this kind of thing procedurally and study the math parallel to it. The math will come back around to the procedure. Cool. So that's lecture for today. Give me 1 second.